We're next going to have as our identity, the first of the speakers in our identity section, Ashok Goel, and he's a professor of computer science and cognitive science in the School of Interactive Computing at Georgia Tech. He's the director of the school's Design and Intelligence Laboratory, and he's co-director of Georgia Tech's Center for Biologically Inspired Design. I think you're going to really be fascinated, though, by what he wants to talk about today, because it has nothing to do necessarily with that computer-assisted design. Today, he wants to talk to us and ask us the question, does our future require us to go back to nature? Please welcome Dr. Ashok Goel.
Thank you. So we all know about the sustainability crisis. We know about global warming. We know about climate change. We know that as the world's population rises and levels of prosperity increase, so does the level of consumption and level of waste. We know that waste is polluting our earth. We know all of this. In our heart, each one of us knows that our society, our species, is facing a problem. What are we doing about it? Several years back, my two children asked me the same question. I have two sons, 19 and 16 years old. And as you can see from the silly grin on my face here in this picture, I'm always happy when we are together. So when they were 9 and 6 years old, we used to spend quite a bit of time in front of the Disney Channel watching nature shows. And sometimes I would wonder whether the earth will be the same when they grow up to be as old as I am. When Albert Gore's An Inconvenient Truth was released, I got a copy of the DVD. And we saw it together. And we were appalled to see what human consumption and waste were doing to the earth. So my children turned to me and asked me, Dad, can't you do something about it? As if Dad knew what to do. So I am a computer scientist and a cognitive scientist. I do research in artificial intelligence. What has AI got to do with sustainability? So let me share a little bit about what I do in my research so that you can see how I try to build a connection between AI and sustainability. For the last 25 years, I have been building AI theories of computational creativity. By creativity, I mean novelty. I mean insight. I mean surprise. In particular, we have been exploring 4 themes: systems thinking, analogical thinking, visual thinking, and meta thinking. And I'll go through each one of them very quickly. So systems thinking is thinking about connections between things. Let's take an example. Lake Claramere is a small, nice little lake in the middle of Atlanta. In 2005, all the fish in the lake were found dead. People looked for causes, but there were no visible clues. Experts were brought in. The insight into the problem came when the experts started looking at the invisible processes of how sunlight makes algae grow and how algae consume all the oxygen that is needed by the fish. I think insight is a process of making the invisible visible. But human mind tends to focus only on the visible structures, like fish and algae. So we developed AI tools that help humans discover and understand the invisible processes, like the sunlight making algae grow and the algae consuming all the oxygen. Cognitive scientists believe that analogical thinking is the single most important process of creativity. Analogical thinking is thinking about novel situations in a manner similar to familiar situations. So analogical thinking is connected with novelty. A famous example comes from physics. About 100 years back, physicists were intrigued by the question of why don't the electrons collapse into the nucleus? In analogy to their understanding of the solar system, they hypothesized that electrons must be rotating around the nucleus. To me, that's extremely creative and very surprising. Electrons rotating around the nucleus? So analogical thinking has to do both with novelty and with surprise. Novelty, surprise, insight. So we developed AI programs that can now do creative analogies on their own. Here is a third fundamental process of creativity, visual thinking. In my opinion, visual thinking is thinking in pictures. Let's consider this problem. This is a problem similar to the problems that appear in the Raven's test of intelligence. That's the most commonly used test of intelligence across the world. You may have taken it yourself. Here is a 3x3 matrix at the top half of the figure, and at the bottom right is a missing entry. You're given 8 choices in the bottom half of the figure, and you have to pick one that can go in the top half in the matrix to complete the matrix. I'll give you a few seconds to think about it. What do you think is the right answer? Any suggestions? 3 is correct. So we have now developed programs that can think in pictures and pass the Raven's test of intelligence. Think about it for a second. AI programs that can think in pictures, take intelligence tests, and do as well as humans. Meta-thinking is yet another process of creativity. Meta-thinking is thinking about thinking. You and I don't just think about the physical and the social worlds around us. We also think about our own thoughts, our goals and plans. We introspect on our beliefs. We reflect on our decisions, especially when the decisions lead to unhappy results. So we build computer programs, AI programs, that can reflect and introspect on their thinking. These programs play certain kinds of interactive games, and they make a series of moves on these interactive games that can sometimes lead to failures. And when they meet a failure, then they think about their thinking and modify it. So let me summarize this part of our conversation. For 25 years, I had been working on AI. I thought I was doing cool stuff. My kids were not impressed at all. They wanted to know what was I doing about sustainability. So as I was searching for how to connect my research with sustainability, I came across this notion of biologically inspired design. Now, the idea of biologically inspired design is not new. We know that Da Vinci created drawings of flying machines inspired by the bat's wings. We know that the Wright brothers tried to create airplanes inspired by the way birds fly. Note that biologically inspired design is very creative. It involves analogical thinking, going from biology to technology. It involves systems thinking. You have to understand both the biological system and the technological system. It involves visual thinking. The visual similarity between Da Vinci's drawings and the bat's wings is pretty clear. It also involves meta-thinking. The designer is not just designing the product. He or she is also designing the design process that results in the design of the product. Once I recognized that biologically inspired design was creative, I could immediately see how my research could help it. It was also fortunate that one of the prime rationales for biologically inspired design is sustainability. So nature contains billions of designs. These designs are at the level of molecules, at the level of organisms, at the level of ecosystems. They have been around for billions of years. Janine Benyus at Biomimicry 3.8 Institute has long advocated the use of nature's designs to create technological products because designs based on biological principles tend to be more sustainable. Almost all of technological design throughout the history of design has been based on the principles of physics. But you can apply the principles of physics in many, many patterns. Biology, through its evolution, has already discovered many of these design patterns that are more sustainable. So why not use them? Let me take a specific example. So windmills were invented about 2,000 years back. They convert wind energy into mechanical energy. Modern windmills also convert that mechanical energy into electrical energy. Recently, Frank Fish, a marine biologist, was studying the hydrodynamics of humpback whales. And he realized that the tubercles on the flippers of these humpback whales allow it to turn at very sharp angles. So the visible structure, tubercles on the flippers of the humpback whales, result in an invisible behavior, the delaying of stall, that results in a visible function, attack at a sharp angle. Inspired by this, a Canadian company called Whale Power is now making turbine blades designed with tubercles on them. That's shown on the bottom right of this figure. Test of these turbine blades shows that they increase the efficiency of windmills, thereby making it more feasible and less costly. I can give you lots of such examples. I'll give you one more. Namibia is a mostly desert country in South Africa. So water is a scarce commodity. There is a Namibian beetle that harvests water out of fog. It has hydrophilic surfaces on its back. And once biologists understood that, then they decided that they could build systems, devices, that could harvest water from fog for humans. And now Dow Chemicals, among other companies, is building these fog harvesting devices that you can buy for a few $100s, and they can help irrigate your plants. So biologically inspired design then can help sustainability. But there are two major problems. One, it works mostly by serendipity. Somebody somewhere comes up with some notion of biology, and it takes many years before a connection to technological product gets made. It's by coincidence, it's by accident, it's not by deliberation. Can we not use AI to make this a principled design methodology? Second, it takes a very long time, tens of years, hundreds of years. Must innovation always take hundreds of years? Can we not use AI to speed up the process of innovation? So let me summarize this part of the conversation. Biologically inspired design seems like a very promising paradigm for sustainability. But at the present time, there is no science of biologically inspired design. Can we develop one? In 2005, my colleague at Georgia Tech, Janet Yen, started what was at that time perhaps the world's first college-level semester course on biologically inspired design. With her help, we have studied this process extensively, and we have found lots of discoveries. Designers and biologists have different mindsets. They speak different languages. Designers are experts at design, not at biology. Biologists are experts at biology, not at design. It takes an enormously long time. It's very labor-intensive and time-consuming to search for biological analogs relevant to a design problem. That's partly why biologically inspired design is so slow. And then we came across a surprise, a big surprise for us. If you take any textbook of design, of technological design, any textbook you wish, you will see a design process a little bit like the process in the top half of the figure. Design always begins with a problem, and the process is problem-driven. To our surprise, that's not how biologically inspired design works. Biologically inspired design often begins with a solution, and then you go about finding a problem to which you can apply it. So the humpback whale is a good example of that. Somebody came up with a solution about tubercles, and they looked for a problem to which it can be applied. This kind of understanding of biologically inspired design already is having an enormous impact on the way we teach biologically inspired design at Georgia Tech. But our goal was to try to systematize biologically inspired design, to make a science out of it. And that's what we have tried to do using AI. Let me take an example. Water desalination. Access to clean water is a major issue across the globe. And we have a very nice solution: desalinate ocean water. So let's put desalination into Google. And by the way, this is real. I have tried this. I did not make this up. So on the left here, on the top here, is desalination at the top, over there. And these are all the entries that are coming from Google when you type in desalination to Google. There's something like 7 million entries. That's very impressive. But every single of the entry, insofar as I can tell, every single of the entry has to do with conventional techniques for desalination. Now, the conventional techniques for desalination require the construction of large plants, and they are very costly. This is a missed opportunity, because it turns out that nature contains a very large number of organisms that do water desalination naturally, very efficiently. Mangrove trees, desert mice, desert scorpions, desert snails, homing pigeons, the roadrunner of our old cartoon movies. So why doesn't Google provide access to these designs? Why not think outside the box? What if we thought we could create a new kind of search engine that, when you give it the word desalination, it brings not just the designs that Google brings, but also the designs of biological organisms that achieve the same function. So we built a prototype of this in our lab. So in this, again, we are typing here desalination, and now what you get out of here are access to biological articles that describe mangrove trees and Peruvian mice and all of those things in biology that occur in nature that already do desalination in a very, very efficient manner. The reason this works, this is analogical matchmaking going on instead of literal search. The reason this works is because we have developed a shared language between design and biology. The shared language understands that desalination is a kind of function. And it also has knowledge about the biological organisms that achieve function of desalination. But of course, it's not enough to just provide access to things. We said earlier that designers are experts at design, not at biology. So if you just provide them access to things, they will still not understand the biology articles. And no designer will use a biological idea unless he or she deeply understands that particular system. So then we thought, in addition to providing access to all of these biology articles, could we also provide explanations for the biological systems in a language that designers understand? So we built a prototype. This particular prototype, on the right-hand side, provides an explanation. So this particular is for a particular gallbladder that also does certain kinds of water treatments. And on the right-hand side is an explanation of how that particular system achieves the function. You can zoom into this to any degree of detail you want, and it will show you this is how this system works. We have done a series of controlled experiments to find out whether this technology actually works. And what we have found out is that A, it provides access to biological organisms when you're looking for a design function. And 2, it helps designers understand the biological systems way better than any of the current search engines do. So this is a new kind of search engine, and this is both an attempt to understand biologically inspired design and to support its practice, to systematize it, so that it doesn't happen by serendipity, so that there is a deliberation involved in it. Any time you're looking for a technological product, you can go to a search engine and find biological organisms that will help you. So let me end this talk by summarizing 5 takeaway points. First, AI is strong and well. Over the last 25 years, AI has made enormous progress toward understanding creativity, towards understanding the nature of novelty, of insight, of surprise. We have computer programs now that can address some of these problems. Second, biological inspired design is a very powerful paradigm for sustainability. It's a call for return to nature, which was the title of the talk. But it's a call for return to nature in a different way. We're not asking that we all go to a primitive pre-industrial society. Instead, we are asking that we invite nature into our world. That whenever we do technological design, we seek nature and nature's principles. Third, while biologically inspired design is very promising, we need to make a science out of it. AI offers powerful techniques for doing it. It already has led to deeper understanding of biologically inspired design. It already has led to tools and information services for supporting it. And it already has had an enormous impact on the way biologically inspired design is taught at universities. Fourth, it's not enough to do these things at universities. We have to take them to the industry at large. Over the last few months, supported by an NSF grant, that's exactly what we have tried to do. But when we talk to industry, we find that industry is consumed by other priorities. To you and me, sustainability and innovation are critical, urgent, obvious. To industry, they're risky, they're costly. So it will depend on our collective action and our collective will to persuade industry to follow, to adopt some of these new technologies. Fifth, you and I both know that sustainability is a very big problem. AI and biologically inspired design probably will be only one small part of the mix of solutions we'll need for sustainability. But I do believe that they are part of the solution. And now I can look my children in the eye and say, we are sorry for what we have done to this earth, but I am doing something about it. So I want you to imagine with me, please. Imagine a world in which every single technological product were designed following the principles of biology. Please imagine with me a world, an earth, on which man again lived in harmony with nature. Thank you.
Thank you, Ashok. Thank you so much for. I was thinking as you were talking about how difficult it might be for a designer and a biologist to find some common ground. Where do you see kind of these spaces, though, where we can influence each other?
Everywhere.
Everywhere. Just meet up.
Just meet up. So sometimes one can think, I'm sure many people here know about the Hitchhiker's Guide to Galaxy.
Oh, yeah.
And there was a babble fish that you could put in your ear, and you could suddenly understand all the aliens. AI is like the babble fish. So there's a new role for AI. We're not building intelligent robots who will take over the world. That's not our dream. Our dream is to put this babble fish so that we will communicate with each other like this.
Very good. Thank you so much.
Thank you.